Hi guys, so today I will be doing number 47 from page 225 in the AP Physics textbook. So the problem reads, an Atwood's machine consists of two masses. Mass A is 65 kilograms and mass B is 75 kilograms, connected by a massless inelastic cord that passes over a pulley free to rotate. The pulley is a solid cylinder of radius, which is 0.45 meters, and a mass of 6 kilograms. Determine the acceleration of each mass, and what percent error would be made if the moment of inertia of the pulley is ignored. Hint: tensions force tension A and force of tension B are not equal. We assume that moment of inertia is equal to 0 for the pulley. So this is our pulley, and this is showing how the force of tension is going up for this mass and the force of tension is going up for this one, but the velocity is going up for this and the velocity is going down here. So how I would start this problem was I would make a force diagram. So for A, I would say we have a force of gravity going down, and we have a force of tension going up. But we cannot assume that they're equal. So then we know that we're going to make this probably negative and this positive because we know that the velocity is going up, so that's why this one should be positive. So when you write your equation, you're going to have force of tension A minus force of gravity A, and you're going to have mass of A equals acceleration. So that's for A. Then when we have B, we do the same thing, except this time the force of gravity of B is going to be positive because the velocity is going down. And then when you go up for the force of tension, it's going to be negative. Once again, because the velocity is going down here. So then when you write the equation, you have force of tension of B, which is negative, plus your force of gravity B, which is equal to, this time, your mass and acceleration are going to be negative here because remember how it's going in the downward direction. So you're going to have mass of B and then acceleration. So once you have those two equations, then you're going to have to think of what equations do we have to know for this. Well, we know that torque is pretty much the same thing as force times the perpendicular force times the radius. Or we could just say force times the displacement. And we know that torque is also equal to moment of inertia times angular acceleration. We also know that linear acceleration, which is what we're looking for each mass, so we're going to need this, is equal to angular acceleration times your radius. And then we know that this isn't provided, but they're always going to provide this to us, that the moment of inertia for a disk is going to be 1/2 mass times r squared. So they're going to provide this, but they didn't for this problem, so I searched it up, and that's going to be our moment of inertia equation. So to start off this problem, what I do first is that I know that I take my first equation over here, F times D, and we know that torque is equal to force times D. So what I'm going to do first is I'm going to be like, okay, what can I put in for my force? Well, I can take these equations in, and I can actually end up putting them in, right? So I can do force TB minus force TA, and then I can multiply it by our displacement. So how did I do that? Well, I know that it only takes into consideration the perpendicular forces. So it's only going to take into our consideration our forces that are going up. Now remember how for this one we're making this, since we're making this positive, we're going to switch the signs. So then I know that I'm going to do it like that because these are the only two perpendicular forces that are going up. So those are the ones we're going to take into account. So once I have that, I know that, and then I know that torque is also the same thing as moment of inertia times angular acceleration. So that's what I can set it equal to. And why I did that is that I know that the I know that the moment of inertia and the acceleration is the same thing as mass times acceleration, which is how we would write like an equation like this. So this is pretty much saying like the same thing. So then what I would do is that I want to like solve for normal acceleration, right? So that's when this equation comes into play, because I know that acceleration is equal to angular acceleration times r tangential. Just making that clear. So what I'm gonna rearrange this equation, right? We know that a is equal to say angular acceleration times r, and I'm gonna solve for I'm going to solve for angular acceleration so I can plug this in. So divide by radius, I divide by radius, and I get this, and I do acceleration over radius. So then I can plug this in over here. And I have negative FTB plus FTA is equal to over radius. So then, once I have that, well, what I'm going to do is that I know that when I want to like isolate acceleration, right? So I know that D, first of all, is the same thing as R, right? Like what I was talking about before. You can either use R or D. So I'm going to just change this to R so that all my variables are like the same. And then what I'm going to do is I'm going to get rid of the R. So I'm going to have negative FTB plus FTA r squared equals I times acceleration. And we can divide by I as well. So once I have that, I get here. And I know like from the past, I know that acceleration is equal to force times mass. And if you don't know how to get that, you have to think of the equation and how we just solve for acceleration there. So once we have that, I know that we want all my forces to be in the top, but I also know that force is equal, right, to mass times acceleration. So we want our masses times our g. So we're going to convert these into our masses, which we're going to use from these equations. So we want to rearrange these equations so we can put them back into this. And then we want our denominator to just be our masses. But we also have our inertia here, or moment of inertia here, so that's also going to be part of it so that we can solve for acceleration. So I'm going to try to move this into the denominator as well. So then I'm going to get okay, and then I'm going to have just acceleration. So that makes that a lot easier. So now I need to figure out what to substitute in. So going back to these initial equations over here, right, I'm going to solve for FTA. So I'm going to have FTA is equal to MA plus FGA. And then same thing for B. So I'm going to have MBA minus FGB. So once I have those, I'm gonna just substitute them in. So then I'm gonna plug this one in, and remember there's a negative, so we have to distribute that in. So I'm gonna have negative ME minus FGB, and then same thing for this. Yeah. So I have that, right? But remember that your forces are going to cancel out here. So this is going to cancel out. And, oh, this one should be negative. Yeah, sorry. This over here should be negative. I didn't notice that. But yeah, that's supposed to be negative, and then you're going to be left with that. Then you want to then you're going to be left with that, and you have your radius, we already moved it down there, right? And we're going to have that equal to acceleration over our inertia, our moment of inertia. So once we have that, we have this, and what we can do is we can have this. And we can take out the g, or like the acceleration, and then we also want to do, remember how we have m in the bottom, right? We want to include our masses down there as well, but we're going to have that negative in place from before over here, right? So we're going to take out that negative, and we're going to have ma plus mb plus I over, oh, we forgot the r squared here, I over r squared, right? So once we have that, we're going to change this we're going to change the moment of inertia using this formula, right? So then we're going to have A is equal to ma minus mb times g over negative ma plus mb plus 1/2 mass times radius squared over radius squared, right? So once we have that, remember that the radiuses cancel, and now we've gotten to a place where we can just substitute everything in, right? So we know that our mass of A is 65 and mass of B is 75. So I'm going to do 65 kilograms minus 75 kilograms. And then I'm going to multiply it by 9.8 meters per second squared. And then same thing in the bottom. And then we have 1/2, and then we're just going to multiply it by the mass of the pulley, which is 6 kilograms, which is what they told me, right? And then you're going to have that. And then if we multiply it all out, we would get point. We would get 0.685 meters per second squared. And that would be the same, that would be the same for both of them. That would be the acceleration of each mass. So that's how we would solve part A. Part B is asking for the percent error made if the moment of inertia is ignored. So to solve that problem, we're going to once again use like our equation of acceleration, which we had come up with. We had acceleration is equal to mass A minus mass B times g over negative mass A plus mass B plus 1 over r squared. And they've told us that when it's ignored, our moment of inertia, when ignored, is 0.7 meters per second squared. So then calculating percent error is just theoretical minus accepted over theoretical. Accepted minus theoretical over accepted. And then we're going to multiply that by 100. So what we're going to do here is actually going to be the acceleration that's ignored minus the acceleration that's not ignored. And by ignored, I mean like ignoring the moment of inertia over the acceleration, over the acceleration that it's ignored. And we're going to multiply that by 100. So we're going to put in 0.7 minus 0.65 over, or 0.685 over 0.7, and we're going to multiply that by 100, and we should get 2.14%. And that would be our percentage error. So that's how you would solve this problem. It takes a lot of steps and a lot of substitution and work, but this problem was